Hello, welcome to another module in this massive open online course. So, we are looking at the L infinity ball. Alright, we have defined the L infinity norm, which is the maximum of the magnitude of the different components of a vector x bar, and let us now look at continue our discussion on the L infinity ball. So, we are looking at the L infinity ball, which is simply defined as the infinity norm of a vector less than or equal to 1. Let us consider a simple scenario, a two dimensional vector x bar which has two components x1, x2, okay. And now the L infinity norm, that is, if you look at the L infinity norm, that will simply be the maximum of magnitude of x1 comma magnitude of x2. Now, L infinity norm less than or equal to 1 implies this maximum of the magnitude x1 comma magnitude x2 less than or equal to 1. This implies that now, since the maximum of two quantities less than or equal to 1, this implies that each of the quantities has to be less than or equal to 1. Now, magnitude x1 less than or equal to 1, this implies that minus 1 less than or equal to x1 less than or equal to 1, that is x1 has to lie between minus 1 and 1, and further magnitude of x2 less than or equal to 1 implies minus 1 less than or equal to x2 less than or equal to 1. And now, so this is the intersection of these four. In fact, if you can see, there are four half spaces. One is given by x1 less than or equal to 1, that is, this is the first coordinate x1, x2. So, let us say this corresponds to your hyperplane x1 equal to 1, and then on the opposite side, let us say this corresponds to the hyperplane x1 equals minus 1. The strip in between denotes the region minus 1 less than or equal to x1 less than or equal to 1. And similarly, this corresponds to the hyperplane, x2 equal to 1, and this corresponds to the hyperplane x2 equals minus 1, and now the region which is between these hyperplanes, this polyhedron, is in fact what is your L infinity, that is, the square is the L infinity ball. So, L infinity ball equals square, this is also a square with sides that are parallel to axis. Okay, the sides are remember, the L1 square had the diagonals that are, if you look at the L1 square, that had the diagonals along the axis, and the L infinity square is the normal square that you would imagine, which has the sides that are parallel to the sides that are parallel to the axis. So, this is your L infinity ball, looks like a square. Okay. So, this is something very interesting, because normally when you think of balls you think of circles and spheres, but if you look at the L1 norm ball, alright, which is a tilted square, and the L infinity norm ball, which is essentially a square. Alright, so these are also norm balls. That is, when you generalize the definition of a norm ball, you can derive these kinds of norm balls, which are very interesting shapes. Okay, and we also have this notion of an L0 norm, which is very interesting. And well, what is the L0 norm? L0 norm, and the L0 norm, you can essentially show that if you look at a vector, what is the L0 norm? That is, the definition is, you can show that norm x bar 0 equals the number of non-zero this is equal to the number of non-zero elements of x bar. This is very interesting, the number of non-zero elements of x bar. So, if you minimize the L0 norm, alright, and this is a very important idea, if you minimize x bar of 0, this results in a large, large number. So, what you will observe is large number of components of x bar will be 0. So, you will get a vector x bar typically in which a large number of its components are 0, because the L0 norm is the number of non-zero elements, implies, and this such a vector x bar which has a large number of non-zero elements, such a vector x bar is termed to be, it has a very interesting name, this is known as a sparse vector. Alright, similar to what we are, similar to the usage, a sparsely populated area essentially means that there are very few people. So, a sparse vector basically denotes a vector in which a sparse, it is sparsely populated with components, a large, there are only very few non-zero components, and a large number of components are 0. So, it brings to mind some vector like this, which has 0 some component, non-zero. All right. So, what you have is a vector in which large number of elements equal to 0. Such a vector is termed as a sparse vector. Okay, and this is a very interesting property. And what is interesting about this is that is you can show that most signals, most naturally occurring signals, such as be it either music or video or images, although they are not themselves sparse, they are sparse under some appropriate domain. For instance, when you look at either the Fourier transform or the wavelet transform of these signals, they are very sparse, and that is a very important property. So, when you look at most naturally occurring signals, such as either a music signal or video or images, are sparse in some suitable domain. Example, either the wavelet domain or the Fourier domain, that is when you take the Fourier transform, or basically the frequency domain, you can also say. So, they are sparse in some domain, and this can be used for, and this idea is a very important idea which can be used for signal processing and to improve the performance. This important property, that is sparsity, can be exploited for signal processing. This important idea can be exploited as signal processing, and this is termed as compressive sensing. And one of the domains where this is exploited is known as, one of the important areas where this idea is used, compressive sensing. Also this is abbreviated as CS, compressive sensing. This is a relatively new field, in fact a path breaking innovation, I must say, which has gained a lot of popularity in the recent past, wherein you exploit the knowledge that this vector, that is this vector x bar, which corresponds to a naturally occurring signal, is sparse in a certain suitable domain, and that can be used to further, that can be used in signal processing and to further improve the performance, all right, in comparison to other schemes, all right. So this is in fact a breakthrough. This in fact is a how do you put it, it's a breakthrough paradigm, all right. It's a breakthrough framework, or this compressive sensing framework, the framework that exploits the sparsity of the signal vectors is a breakthrough framework that can be used for enhanced signal processing. Right. So, with that, let us complete this discussion. Let us move on to looking at some problems to better understand the concepts. Let us start with a few problems related to the determinants and the positive semi-definite property. So, I will want to start with some examples. To start with, let us start with some simple examples related to matrices and their properties. Let A be an n cross p matrix, and B equals p cross n matrix. The first thing that we want to show is that determinant of In plus AB equals the determinant of Im, or I am sorry, a determinant of In plus AB is the determinant of Ip plus BA. Let us make this n cross m matrix. I think that will make it life much more simpler. So, this B is an, naturally if you are multiplying m, they have to have dimensions that match up. So, this is, we want to show this is an, so In, this is the n cross n identity matrix, and this on the other hand, this is the m cross m identity matrix. Now, the solution is as follows. Now, if you consider, let us consider the matrix, let us consider the matrix P, which is given as In minus A, B, Im. Now, I can perform row operations, or in this case block row operations. Okay. So, let us call this as block row 1 denoted by R1, and this is block row 2 denoted by R2. Now, let us obtain P tilde by performing R2, that is block row 2 minus the matrix B times block row 1. So, you obtain the matrix P tilde, which is basically, well, first row remains unchanged, second row is B minus identity times B, which is 0, I minus of B times minus A, so that is I m plus B A. Now, if you look at the determinant of P tilde, which is equal to determinant of P, now this arises since row operations, since determinant, remember you might have seen a property of determinants before, that is, since determinant remains unchanged in row operations. So, determinant P tilde equals determinant P, and now you see the lower block is zeros, which means the determinant of P is simply the determinant of I n times the determinant of I m plus B A. Now, the determinant of I n is 1 since it is an identity matrix. So, this quantity equals 1. So, this is simply the determinant of I m plus B A. So, determinant of P tilde equals the determinant of I m plus B A. Let us call this as our result 1. Now, let us form the matrix P hat by performing R 1 plus A times R 2 on. So, R 1 goes to, let us write this as follows, R 1 goes to R 1 plus A times R 2. Here we have R 2 goes to R 2 minus B times R. So, on P, and this gives the matrix, you can check, this gives you the matrix, well, this will be I n plus A times R 2, A times B plus I m plus, well, let me just check this, this is an n cross m matrix, B times A, B is m cross n. So, this B times A. So, this will be I n R 1 plus A times R 2. So, I n plus B times A, I am sorry, this will be I n plus A times B, and this will be I n plus A times B, this will be, the other will be minus A plus A times minus A plus A times I. So, this will be 0, and this second row remains unchanged, that will be B and I m. And now, if once again, so this is your P hat, and now if you once again formulate the determinant of P hat, that is going to be simply the determinant, because this is 0, that is going to be the determinant of A n plus A b times the determinant of I m. So, and by the way, again once again this is equal to the determinant of P, because you are performing row operations on P, determinant of I m is 0. So, this will become I n plus determinant of I n plus A b. And finally, from 1 and 2, it follows that determinant of I plus B A equals determinant of I plus A B. Okay. All right. So, this follows from the results in 1 and 2. Let us look at another interesting example, that is example number 2. We want to show that the trace of a square matrix A is the sum of the eigenvalues of A, and the determinant of A is the product of the eigenvalues. So, this is trace which is equal to sum of eigenvalues and the determinant is basically the product of eigenvalues. Okay. And this is, well, to do this you can start with the property, the following thing: for a general matrix, the A can be expressed as U lambda U inverse, all right, where U equals matrix of eigenvectors lambda is diagonal value or diagonal matrix of eigenvalues. Okay. Lambda equals diagonal matrix of eigenvalues, and lambda has the following structure. Okay. If A is an n cross n matrix, lambda equals diagonal matrix of eigenvalues. Assume that A equals an n cross n matrix, square matrix. All right. Now, of course, we have already seen that if A is PSD, then it becomes U equal to U lambda U Hermitian. If A is a PSD matrix, if A equals PSD, while the above is valid for any general matrix A, this becomes U lambda U Hermitian. I am sorry, because U is orthogonal, U is a unitary matrix for a PSD matrix A. U is a unitary matrix and U inverse is simply U Hermitian, because U Hermitian U equals U Hermitian equals identity, which implies that U Hermitian equals U inverse. Okay. But this is only for a PSD matrix. Okay. But we can show the above property, that is the trace is equal to the trace of matrix A is equals the sum of its eigenvalues for any general matrix A, and that is as follows. If you consider the trace of A, you use the eigenvalue decomposition, and now you replace the trace as U lambda U inverse. Now, we know that the trace of AB equals trace BA, that is the trace of that is, you can interchange the product of the matrices, the order of the product in the trace. So, this will become trace of lambda, it is very simple. So, this has become trace of lambda U inverse, if U, this is using the property trace of CD, just not to confuse with A equals trace of DC. Now, U inverse U is identity. So, this is trace of lambda, which is the diagonal matrix of eigenvalues, and this is nothing but summation of I lambda I. Now, similarly, one can also show, now if you look at the determinant of A, that is the determinant of U lambda U inverse, which is now the determinant of product of matrices is the determinant of the product of the determinants, which is equal to the determinant of lambda times the determinant of U times the determinant of U inverse. Now, if you look at the determinant of U into the determinant of U inverse, because U inverse is identity, determinant of identity is 1. So, therefore, determinant of U into determinant of U inverse is 1. This implies this equals the determinant of simply lambda, which is now nothing but basically the product of the eigenvalues. And this is a very interesting property that is frequently used. Pi equals 1 to n, this is the, so you can say determinant of A equals product of its eigenvalues, trace is equal to the sum of its eigenvalues. Okay. Trace of a matrix equals the sum of its eigenvalues. Okay. Now, similarly, you can also exploit this property if you look at trace of a matrix A raised to the power of n, that equals trace of A times A, the product n times. We have already seen this for a positive semi-definite matrix, that becomes U lambda U inverse, U lambda U inverse times U lambda U inverse, that becomes trace of, I am sorry, that becomes trace of, well, U lambda raised to the n U inverse, which is nothing but trace of lambda raised to the power of n U inverse U, which is trace of U inverse U is identity. So, this is trace of lambda raised to the power of n, this is summation over I lambda I raised to the power of n, that is trace A raised to the power of n. And in a similar way, you can show that the determinant of A raised to the n is the product of I equals 1 to n lambda I raised to the power of n. This is nothing but the determinant of U lambda raised to the power of n U inverse, which is how you get this result. Okay. So, these are some interesting properties, in fact very interesting properties that come in handy frequently during manipulation, that is the trace of a matrix A, square matrix A is the sum of its eigenvalues, and the determinant of a square matrix A is basically the product of its eigenvalues. All right. So, we will stop here and continue this discussion by looking at other examples in the subsequent modules. Thank you very much.